Good afternoon, everyone. Thank you for attending this VISSIM webinar. Because Dr. Aty is on traveling, he is not able to present. So I and Yina will give the presentation. It is based on our VISSIM project. The title is the integration of microscopic big traffic data in simulation-based safety analysis. At the beginning, we will explain the big traffic data used in our project. And then we will explain the implementation of the big traffic data in traffic efficiency in the traffic safety evaluation. And finally, we will conduct the simulation test. The first one is based on VISSIM simulation. It tests the safety under fog condition. The second one is Cellular Automaton simulation. It investigates the safety of the dynamic zone. The study subjects are 3 expressways in Central Florida and an intersection close to the University of Central Florida. The third location is on the Interstate Road 4. For the expressway system, it has 2 vehicle detection systems. The first one is the automatic vehicle identification system. The other one is the microwave vehicle detection system. The AVI data, previously the initial objective of AVI system is automatically toll connection. When a vehicle passes an AVI detector, the detector records its tag ID and then connects the toll. Later, researchers and the practitioners use the AVI to estimate travel time. When a vehicle passes two AVI detectors, its travel time can be obtained by calculating its time steps difference at these 2 detectors. Meanwhile, since the distance between the 2 AVI detectors are available, so the space mean speed of the vehicle can be captured. Similar like the AVI system, the MVDS system is point-based vehicle detection. It connects the speed, volume, occupancy at a point. In this project, 2 types of MVDS detector are used. One is based on one aggregate traffic information into 1 minute, and the other one provides disaggregated vehicles information. That means it provides the traffic information for each vehicle. In addition to AVI and the MVDS, camera was also used. 3 cameras were placed at the northbound of the intersection close to University of Central Florida to connect the traffic information and also connect the vehicle stop and go condition during yellow phases. So here you can see the 3 cameras connect all the information of the northbound. For the implementation of the big traffic data, first the traffic efficiency was measured based on the congestion evaluation and the travel time reliability. The congestion is evaluated by the travel time index. The travel time index is calculated using actual travel time and the free flow travel time. The higher the travel time index, the more congestion. Another traffic efficiency evaluation is travel time reliability. It evaluates the percentile variation. The percentile variation is based on the standard deviation of travel time and the average travel time. The higher the percentile variation, the lower the travel time reliability. By evaluating the traffic efficiency of the westbound of State Road 488, it can be found during morning peak hour for the milepost from 11 to 18. It has high congestion and a lower travel time reliability. The traffic safety evaluation is based on real-time safety analysis. it is assumed that the reason why a crash happens is because the disruptive traffic condition just before this crash. So by analyzing and comparing the disruptive traffic conditions, the parameters which are more traffic prone than others can be found, and then use these parameters, the traffic risk, the crash risk can be estimated. In this project, we use 5-minute interval. That means by obtaining the traffic parameters and then estimate the crash risk, the crash risk in the next 5 minutes can be obtained. This figure gives an example just before the crash occurrence. The speed of the number 5 lane is changed dramatically. That may be the reason why this crash happened. The traffic safety evaluation is based on logistic regression model. For a given event, it has 2 exclusive states, crash and non-crash. Then the parameters are used to estimate the crash ratio using the logistic regression model. The traffic safety evaluation is conducted for the mainline and the ramp separately. For the mainline, the result is shown in the table. The positive estimation parameter means when this variable increase, the crash risk increase, and the negative means when this variable increase, the crash risk actually decrease. So, for example, when the congestion index at the downstream station is increased, the crash risk increase a lot. Because when the downstream has congestion, a vehicle needs to decelerate. And if a vehicle decelerates and the following vehicle didn't decelerate in time, then a crash, a real end crash might happen. For the ramp crash risk, it is also based on logistic regression model. So for on a wet roadway status condition, a vehicle is more likely to have a crash because it has a longer braking distance, and the vehicle are more likely to auto control compared to the dry roadway status condition. So the wet roadway status condition increase the crash risk. For the simulation, in order to build the VISSIM simulation network, 2 data are connected. The first one is the traffic data. It is from the MVDS detection. This detector provides the traffic speed for each vehicle, and the visibility are provided by the weather station in the area. The study period is on February 4th, 2014, from 7 to 8 a.m. In this time period, the study location was under fog conditions. The maximum and the minimum visibility are 0.17 and 0.09 miles. In this simulation, there was a parameter called look-ahead distance. The distance defines at which a vehicle could see forward in order to react to other vehicles in front or to the side. So in this project, the maximum and the minimum look-ahead distance will stay the same as the maximum and the minimum visibilities. The traffic input are from MVDS detector. It provides volume, track percentage, and speed distribution. In addition to look-ahead distance, other 3 parameters in VISSIM are also tested. They are headway time, following variation, and the speed dependency oscillation. For each parameter, 4 values are tested. So in total, we have 64 scenarios. For each scenario, we run 3 times. For each time, we state different random seeds. This one is our VISSIM simulation. We put data connection points at the same location of the MVDS detection. detector. So when the data connection point provides the simulated speed and then compared with the MVDS speed, then the simulation is calibrated and validated. The result shows that when the headway is 0.9 seconds, the following variation is 4 meters, and the speed dependency of oscillation is 11.44. The VISSIM simulation is well calibrated and validated because the speed of the field and the speed of the simulation, the difference is minor and is not significant. So after we validate the VISSIM network, we tried different traffic volume and also different speed limits to find the impact of the traffic volume and speed limits on the safety of the network under both conditions. The VISSIM provides a trajectory file, and the files are input in the surrogate safety assessment model. And then the model can provide the conflict information, include conflict time, location, type, etc. So this one shows the results. It shows when the volume and the speed limit increase, the conflict number increase. And when the volume was low, the speed limit had more impact on conflict. See, and when the volume was 4,000 vehicles per hour, and the speed limit are 17 miles per hour. The total conflict is 60.5 times of the conflict when the speed limits are 50. So when the volume was low and the segment is under force condition, maybe decrease the speed limit is a very effective way to improve the safety of the segment. But when the volume was very high, the speed limit has less impact on safety. You see here, when the volume was 12,000 vehicles per hour and the speed is 70 miles per hour, the crash number under this condition is only 1.8 times compared to the speed limit under 50 miles per hour. So when the volume is pretty high, maybe decrease the speed limit is not an effective way to improve safety. Then the simulation is also conducted for the on the cellular automation, and Yina will give the presentation. Okay, thank you, Ling. So now let's look together at the different dilemma zone countermeasure. In general, there are two types of dilemma zone countermeasure. The first type is advanced time warning method, which includes flashing green or flashing yellow. It is usually at the flashing green or yellow phases at the end of green phases. The flashing phases usually more than 3 seconds, and previous study has found that the flashing green or yellow phases may reduce the right angle collision and the severity of maximum acceleration and deceleration, and this countermeasure has been used in many countries. The second type is advanced distance warning method. This method includes a pavement marking countermeasure. It is at the pavement marking signal ahead at upstream of the intersection. There are few practical use in the United States, and in this study, we proposed a new countermeasure which includes both advanced time warning method and advanced distance warning method. And I will introduce this countermeasure in detail later. So this picture shows an intersection with pavement ahead at upstream of the intersection. So when outside of the yellow indication, if the vehicle hasn't passed the pavement marking, he or she needs to stop during the yellow phases. Otherwise, he or she needs to choose go during the yellow phases. During the simulation, we assume all the driver will follow the pavement marking rules. In order to get the driver stop-go decision during the simulation, 36 hours video was filmed and 8 variables was extracted from the video. These variables are distance to the intersection, vehicle's operating speed, driver stop-go decision, elapsed time, red light running violation, lead or follow position, lane position, and vehicle type. A logistic regression analysis was conducted in order to analyze driver stop-go decision, and from this result, we found 3 variables have significant impact on driver stop-go decision. These are lead follow position, speed, and distance. And from this result, we found that if a vehicle is at follow position or have higher speed or shorter distance to the intersection, he or she are more prone to choose go during the yellow phases. So during the cellular automaton simulation, each road is made up of cells, and each cell can be empty or occupied by one car. The car is usually generated from the left side and moving from the left to the right. The car will go through the stop line during green phases, but stop during the red light at the right side. So in total, we have 3 scenarios. The first scenario is the scenario with typical intersection, and the second scenario is the intersection with flashing green countermeasure, and the third scenario is the scenario with pavement marking countermeasure. And these 4 figures show the simulation result of the 3 different scenarios. The first 3 figures show the rear-end crash risk, while the last figure shows the red light running violation risk. As we can see from the first 3 figures, sometimes the flashing green countermeasure may increase the rear-end crash risk, and the pavement marking can effectively decrease the rear-end crash risk. However, when we look at the rear-end red light running risk, we found that sometimes the pavement marking countermeasure may increase the red light running risk, especially when the speed is relatively low. So based on this previous analysis, a new countermeasure is proposed, which is called PMAIC. In this countermeasure, we put a flashing yellow indication next to the pavement marking. If the vehicle speed is lower than the speed limit, the flashing yellow indication will be on site a few seconds before the yellow phases. So if the driver has seen the flashing yellow indication before onset of the yellow signal, even though he or she has passed the signal ahead marking, he or she still needs to choose stop during the yellow phases. So based on this rule, if the vehicle's operating speed is higher than speed limit, which is 45 miles per hour in this study, the scenario will be same as pavement marking countermeasure. But if the vehicle's speed is lower than the speed limit, the flashing yellow indication next to the pavement marking will be unset. If the vehicle wants to pass the intersection during the yellow phases, he or she needs to both pass the pavement marking and haven't seen the flashing yellow indication before onset of the yellow signal. So these 3 figures shows the comparison between the pavement marking countermeasure and the new countermeasure. As we can see that the new countermeasure can further decrease the rear-end crash risk. And during the simulation, rear red light running violation was observed. So based on the previous analysis, we conclude that the flashing green countermeasure may increase the risk of rear-end crash risk, and it does not have a significant impact on reducing red light running risk. And the pavement marking countermeasure can decrease the risk of rear-end crashes, but it may increase the red light running violation risk. And the new countermeasure can decrease both rear-end crash risk and red light running violation risk. That's all for our presentation. If you have any questions, you are welcome to ask. Thank you. Any questions? Yes, we have more macro simulation because for the real-time safety analysis, because we can use the traffic parameter to estimate the crash risk. So in the following steps, we based on the crash risk, and then if the crash, the hazard condition is predicted, we use the ramp metering and the variable speed limit to reduce the crash risk. This one is conducted in the macro simulation VISSIM. And also the new countermeasure for the dilemma zone, it can also work as an in-vehicle device. So this countermeasure can also be tested in a driving simulator. Yeah, that's all done. Thank you. The fog analysis, because in recent years there are two very severe crash happened in Florida area. So that's the reason why we are focusing on the fog-related crash recently. And also for fog, it's very hard to find because the crash are rare events. So it's very hard for us to observe the crashes in field. So, but in the simulation, we can use the conflict information. The conflict has already proven to be highly correlated to the crash. So, if we put all the information in the simulation and adjust the parameters, and then we found the conflict increase, then we can assume the crash number will increase. So that's the reason we use the VISSIM simulation to simulate the fog conditions. Yes. So I explaining this analysis under other crash situations. Actually, we didn't extend for the other crash situation, but we extended this analysis to a congested VISSIM segment because in the downtown area of Orlando, we have a lot of VISSIM segments. Means the on-ramp is very closely followed by the off-ramp. For this VISSIM segment, the safety is a big concern because the on-ramp vehicle will merge to the on-ramp and the off-ramp vehicle will go to the off-ramp, and these two types of vehicles will live in this area. And also under the congestion condition, especially for morning peak hour, the safety of the VISSIM segment will become more serious. So I explained this the real-time safety analysis to the VISSIM segment in the VISSIM simulation. So anyone has other questions? And if you have questions and you cannot ask now, and also if you are interested in the work we have done, and we have already published several papers, you can email us according to the email address we show on the screen. Thank you.